What if I told you one invisible ocean switch near the equator can reshape hurricane season, supercharge Pacific storms, and rewrite weather patterns across the planet? That switch in the ocean has a name, the El Nino Southern Oscillation, or ENSO for short. You've probably seen some viral videos on social media talking about a super El Nino. But what even is an El Nino, and why does it matter? Welcome to Untamed Skies, where science meets humanity, and where we track the atmosphere not to hype the storm, but to understand the forces behind it, so you can tell fact from fiction the next time you're flooded with weather clickbait on social media. El Nino is a classic case of a natural cycle that is prone to hype and clickbait, but understanding it is important because it does have real consequences for how you experience the weather in your daily life. So let's dive in. Start with the tropical Pacific Ocean in its normal state. In this animation, Asia and Australia are on the left, the Americas are on the right. We cut this graphic along the equator so you can see the dynamics from the side. Normally, the trade winds blow from east to west. They push warm surface water toward Indonesia and Australia, piling up the ocean's heat in the western Pacific. That warm water feeds towering thunderstorms, the rising branch of what's called the Walker circulation. Meanwhile, near South America, colder water rises from below. That's called upwelling. It brings cooler, nutrient-rich water to the surface and helps keep the eastern Pacific cooler. In fact, the waters off of Ecuador are so cold that there's a population of penguins that live on the Galapagos Islands right along the equator. So the Pacific is not just an ocean, it behaves like a heat engine. Now, watch what happens during El Nino. Every few years, the trade winds weaken, and sometimes they even reverse for short bursts. Warm water that was piled up in the western Pacific is then able to slide eastward across the equator. The cool upwelling near South America gets suppressed. The warmest water anomalies and all the enhanced thunderstorm activity that follows them shifts toward the central and eastern Pacific. By anomalous, I mean the difference between the actual temperature and the long-term average temperature. If I say it's usually 80 degrees and it's actually 85 today, then the anomaly, or departure from average, is plus 5 degrees. Oftentimes what's plotted in El Nino graphics like this is the anomaly, not the actual temperature. This is an important distinction because even during an El Nino year, the actual temperature of the western Pacific is still warmer than the eastern Pacific. So don't let the anomalous temperature graphics fool you. This will be important later on in this video when we talk about how El Nino impacts tropical cyclones. This shift in the thunderstorms and the Walker circulation is the atmospheric response to the shift in anomalous ocean temperatures. And the jet streams, rainfall patterns, drought zones, and tropical cyclone environments can all shift with it. El Nino peaks during the winter, and we typically see extra dry and warm conditions across the Pacific Islands in Southeast Asia, while the southern United States is cooler and wetter with stormier weather. La Niña is the opposite of El Nino, but really it's more like the normal case except on steroids. Instead of weaker trade winds, the trades get stronger. They push the warm water even further west. Upwelling in the central and eastern Pacific intensifies. The maximum thunderstorm activity pushes back toward Indonesia and the western Pacific and into the South China Sea. So in summary, El Nino relaxes the trade winds and the warm water in the western Pacific spreads eastward. La Niña strengthens the trade winds and pushes the warm water even further west. So why do scientists call this ENSO? Because El Nino and La Niña are not just ocean events. They are coupled ocean atmosphere events, meaning the ocean and air above it affect each other in this closed feedback loop. The name El Nino came from fishermen along the west coast of South America, who noticed that every few years unusually warm water reaches the surface of the ocean and shuts down fishery stocks, because there's usually more fish when there is cold, nutrient-dense water being upwelled. They noticed that this anomalous warming happens near Christmas and called it El Nino de Navidad, the Christ child. Then in the early 1900s, scientist Sir Gilbert Walker discovered a giant pressure seesaw across the tropics. When pressure was higher in the region near the island of Tahiti, it tended to be lower near Darwin, Australia. He called that pattern the Southern Oscillation, and the difference between Tahiti and Darwin was known as the Southern Oscillation Index. Later, Jacob Bjerknes helped connect the dots. The warm ocean changes and the atmospheric pressure and wind changes were part of the same coupled system. So El Nino plus Southern Oscillation equals ENSO. It has three phases: warm phase, cool phase, and neutral. The warm phase is El Nino, and the cool phase is La Niña. The neutral phase is closer to normal when neither El Nino nor La Niña is dominating the pattern. Now, let's talk storms. ENSO doesn't directly create or destroy a tropical cyclone. It loads the dice. During El Nino, the central and eastern Pacific usually become more favorable for tropical cyclones. Wind shear often relaxes there, rising motion increases, and storms have a better chance to organize. But in the Atlantic, El Nino often does the opposite. With the Walker circulation shifting eastward, stronger upper-level winds increase vertical wind shear, and as you learn from this video here, wind shear can rip developing hurricanes apart before they reach peak intensity. That's why El Nino seasons often favor more activity in the central eastern Pacific and less activity in the Atlantic. But that said, even though we expect fewer tropical cyclones in the Atlantic during El Niño years, this says nothing about landfall potential. So all it takes is one hurricane hitting a populated area to cause a major disaster regardless of how many storms happen that year. Think Hurricane Andrew that devastated the Miami area. 1992 was one of the quietest Atlantic hurricane seasons on record, but it still produced a Hurricane Andrew. In the western North Pacific, where mature tropical cyclones are called typhoons, El Niño can shift the formation zone farther east, closer to Micronesia to the east of Guam and the Marianas, and farther from the Philippines. That gives the storms more open water and more time to intensify before moving west. So although the frequency or total number of western Pacific tropical cyclones don't change because of ENSO, thanks to the already warm water over there even during an El Niño year, as we talked about earlier with the concept of anomalies, the ones that do form have more time over a tropical ocean to intensify. This is why El Niño years often feature more intense tropical cyclones in the western Pacific, and places like Guam and Saipan get threatened by more intense typhoons. During La Niña, the Atlantic becomes more favorable because wind shear tends to relax. The central and eastern Pacific often become less favorable. And in the western North Pacific, storm formation tends to shift back westward, increasing storminess for the Philippines, the South China Sea, and East Asia. That doesn't mean every El Niño or La Niña behaves exactly as described here. Instead, think of ENSO as the background signal that loads the dice, tilting the odds toward one of these scenarios. For more weather science without the hype, subscribe to Untamed Skies, where Mother Nature stays untamed, but not unexplained. Drop a comment with what else you'd like to learn, and keep looking up.